Welcome back to the deep dive. So our mission today, it's a big one. We're going to take the stack of sources that detail an almost impossible life.
It really is. We're talking about a man who arrived at the front lines of mathematics having never really studied the rule book.
Exactly. And our job is to extract the insights that explain not just what he did, but how. We are diving into the extraordinary life and, frankly, the shocking mathematical legacy of Srinivasa Ramanujan.
Yeah, we're looking at a true mathematical anomaly. Srinivasa Ramanujan, born in India, 1887. He was a figure in the early 20th century whose whole career, his entire life, it just defies every standard academic story we know.
It does.
The journey he took from, extreme poverty in Madras all the way to the very rigid formal halls of Cambridge. It's just this powerful testament to raw, undiluted genius.
Okay, let's unpack that right away. Let's define the central paradox here because the sources are so clear on this. Ramanujan had almost no formal training in pure math. No access to modern European textbooks, no degree, no rigorous instruction in things like complex analysis. And yet, he made these huge contributions to some of the most difficult fields out there.
Number theory, infinite series, continued fractions.
Right. And he was solving problems that established academics, the best in the world, they considered them completely unsolvable.
It's an unprecedented achievement.
Yeah.
And when you look at the sheer output, the numbers themselves are almost unbelievable.
Let's get into that.
Ramanujan independently compiled nearly 3,900 results. We're talking mostly identities and equations, all recorded in his famous notebooks.
And the really astonishing part.
The astonishing part is that the vast majority of them over the decades have been proven correct. And so many of them were completely new, opening up research areas that are still defining modern math today.
Can we just stop there for a second? 3,900.
It's mind-boggling.
I mean, you have to put that in perspective for someone listening. A typical PhD thesis in pure mathematics, what does that have? 5, maybe 6 major provable results.
If you're lucky, yeah.
And Ramanujan generated 3,900 of them in isolation with no formal proofs attached.
Exactly. And that context is precisely why his early attempts to get noticed failed.
Right.
As Hans Einstein pointed out, he couldn't get the attention of leading mathematicians at first because his work was, and I'm quoting here, too novel, too unfamiliar, and additionally presented in unusual ways.
They didn't know what they were looking at.
Not at all. They'd look at his equations and couldn't even figure out what branch of math they belonged to, let alone start to verify them. His genius was so far outside the established framework that, to them, it probably just looked like nonsense.
It's this classic clash, isn't it? Intuition versus rigor, East versus West. So, our mission today is to explore 2 key ideas. First, how did the solitary genius find his voice through that extraordinary partnership with G.H. Hardy?
A crucial relationship.
And second, how do his insights continue to inspire such profound research? I mean, we're not talking about dusty historical facts here. We're talking about things, mere comments in his writings, that researchers were still uncovering and proving as profound number theory as late as 2012.
His work is a perpetual mathematical goldmine. It really is.
So let's go back to the beginning of this incredible story, the isolated prodigy. Srinivasa Ramanujan was born December 22, 1887, in Erode, India. He was from a traditional Tamil Brahmin Iyengar family in what was then the Madras presidency of British-ruled India.
And his roots were very modest. His father was a clerk in a small shop. His mother was a housewife who also sang at a local temple.
And she'd often take him with her, right? Which gave him this really early, strong connection to spirituality that we'll see come up again and again.
Absolutely. And his childhood, it immediately signaled that this was no ordinary mind. The sources say that by age 11, he had completely exhausted the mathematical knowledge of 2 college students who were boarding at his family's home.
Just to think about that. These are guys studying for higher exams, and this 11-year-old kid is basically running them out of things to teach him.
Until they had nothing left to give. It's an incredible developmental leap. Most kids that age are, struggling with fractions.
And he's already pushing into university-level concepts, and it didn't stop. By age 13, he gets his hands on a book by S.L. Looney on advanced trigonometry.
And this wasn't some simple textbook. Looney's book is a real challenge, even for university students at the time.
But Ramanujan doesn't just master it. He starts discovering his own sophisticated theorems, completely independent of any curriculum.
He was just a natural problem solver. He had this high aptitude for logistics, too, even as a teenager.
Oh, the school scheduling problem.
Exactly. The story goes that when he was 14, he helped his school solve this really complex scheduling challenge. how to assign 1,200 students to about 35 teachers.
That's not just arithmetic, that's a complex optimization problem. It shows he had this innate, practical, applied intelligence long before those fields were even properly formalized.
It does. But the really crucial text, the one that shaped his whole unique methodology, was a book by G.S. Carr.
A synopsis of elementary results in pure and applied mathematics.
That's the one. He got a copy in 1903 when he was 16, and it fundamentally changed how he approached mathematics.
So what was this book? It wasn't a normal textbook, was it?
No, not at all. It's arguably the single most important document in his entire development. It was this massive 2-volume collection of about 5,000 theorems and results.
Wow.
But, and this is the key part, they were stated largely without any detailed proofs or derivations.
Just the answers.
It's just the final answers. Carr designed it to be a memory aid for students cramming for exams. It gave you the destination without showing you the route.
So imagine you're a 16-year-old prodigy, and you get a book with 5,000 mathematical final answers, but no explanation of why they work.
And because he studied it so intensely, line by line, he internalized this method where intuition and the final result were everything. The formal proof was, well, secondary. Or maybe just something you didn't need to write down.
And that's the period of isolated discovery, right, where he has to invent the steps and the proofs himself. This is why he later struggled so much with the Western demand for rigor.
Absolutely. And yet, even completely on his own, his mind was just exploding with discoveries. He independently developed algorithms for Bernoulli numbers. He calculated the Euler-Mascheroni constant to 15 decimal places.
That's just world-class analysis.
Performed by a young man with no formal guidance whatsoever.
Which brings us to the tragedy of his academic career.
Okay.
Because despite this obvious genius, his formal performance was a complete disaster.
A total disaster.
Yeah.
He got a scholarship to Government Arts College, but his obsession with math was so all-consuming that he neglected everything else. He failed every other required subject.
Especially English and physiology, the sources say.
He literally couldn't force his brain to care about anything that wasn't mathematics.
Yeah.
So the scholarship was revoked instantly.
Yeah.
And that was followed by this long, dark period.
He failed his Fellow of Arts exam multiple times, left college without a degree. And this isn't just an academic setback. In that rigid colonial system, not having credentials meant extreme poverty.
Real poverty. The sources describe him as often being on the brink of starvation. This wasn't a struggling student with a support system. This was genuine economic desperation.
And it was made worse by his refusal to work in any field that wasn't math. It took until about 1910, he's in his early 20s, newly married,
To his wife, Janaki.
that he begins this systematic search, not just for a job, but for mathematicians who could actually understand what he was doing.
And that search leads him to V. Ramaswamy Iyer, the founder of the Indian Mathematical Society. And Iyer was just instantly struck by the power and originality in Ramanujan's notebooks.
And Ayer made a crucial decision.
A really humane and critical decision. He later said he had, quote, no mind to smother his genius by an appointment in the lowest rungs of the revenue department.
In other words, he refused to let this talent get buried in bureaucratic paperwork.
Right. He became his crucial early advocate. He helped him get letters of introduction to European scholars, and importantly, helped him secure a small research scholarship, about 75 rupees a month, at the University of Madras.
That small bit of recognition, and Ayer's refusal to just give him a menial job, it really saved him from being lost to clerical obscurity. It saved his genius. But even with that small grant, the financial pressure was still immense. The sources detail it clearly, especially after he married Janaki in 1909 and then had to recover from surgery for hydrocele testis. He needed a stable income.
So he eventually secures a post as an accounting clerk at the Madras Port Trust. He's earning a very meager 30 rupees a month.
The irony is just, it's incredible. The man who would redefine number theory is working as an accountant.
But what's so telling is that he would finish his clerical work easily, very quickly, which left him with all this spare time for his actual research. And his colleagues and his boss, they supported him. They recognized his unique focus.
That support was absolutely vital. It let him continue his true work, which brings us to the moment that changed absolutely everything. The letter to Cambridge.
Before G.H. Hardy, though, Ramanujan's work went through what you could call a rejection filter.
Right, he'd sent it out before.
Yes, his manuscript pages were sent to several established British mathematicians, and they failed to recognize what they were seeing.
The sources cite a couple of examples.
J.M. Hill, a prominent mathematician, sent the papers back with this incredibly condescending comment that they were riddled with holes and that Ramanujan lacked the necessary educational background.
Wow.
And even worse, H.F. Baker and E.W. Hobson, both very respected names, they just returned the work. No comment at all. It was so unconventional, they didn't even think it was worth a rejection letter.
So, 3 strikes. It wasn't until January 1913 that he wrote to G.H. Hardy at Cambridge. And Hardy was, well, arguably the most brilliant and rigorous mathematician in Britain at the time.
And he receives these 9 pages of complex handwritten mathematics from a completely unknown clerk in India.
Hardy's initial suspicion must have been off the charts.
Oh, absolutely. It was warranted. He got unsolicited manuscripts all the time, usually from cranks, claiming they'd, trisected the angle or something. His first reaction was that it was probably a fraud or the work of a lunatic.
But that suspicion, it quickly changed into something else. He and his colleague, J.E. Littlewood, started looking at the work more closely.
And Hardy later confessed that, yes, some of the theorems were recognizably advanced, which confirmed Ramanujan had genuine talent. But the others, the truly novel results, he said they defeated me completely. I had never seen anything in the least like them before.
It was that sheer novelty, the fact that they had no traceable lineage in Western mathematics, that forced Hardy to reconsider.
And this brings us to that famous quote, the one that basically validated Ramanujan's genius for all time. Hardy concluded that the theorems
must be true, because if they were not true, no one would have the imagination to invent them. That quote is just. It's pivotal. It's the ultimate recognition of pure intuition. The idea is so beautiful and strange that it can't be a mistake. It has to be a revelation. It took a genius like Hardy to recognize a genius that looked nothing like himself.
And let's get into the specifics of what convinced him, because it really shows the technical gulf Ramanujan had bridged on his own. The sources mention a complex infinite integral formula.
But it was the infinite series for pi that really blew Hardy away, wasn't it?
It was. For the listener, an infinite series is just a way to express a number by adding up an infinite sequence of smaller and smaller terms. Ramanujan's series for, specifically, 2-piler, was derived from something called a hypergeometric series.
Yeah.
It was completely new to Hardy.
And he said it was much more intriguing than even the work of giants like Gauss and Legendre.
Yes, and it's a masterpiece of technical complexity. But what makes it so groundbreaking is its convergence rate, how fast it gets you to the answer.
Right, let's slow down on that. What does that actually mean, extraordinarily rapid convergence?
Well, if you use the older standard methods, you need thousands of terms to get, say, a dozen decimal places of pi. But with Ramanujan's formula, if you just take the first 2 terms of the sum,
Just 2.
just the first 2, you get a value that's already correct to 14 decimal places.
Wow.
That phenomenal efficiency is the basis of some of the fastest algorithms we use today to calculate pi. It shows he wasn't just generating true ideas, he was generating ideas that were computationally superior.
So after this, Hardy immediately starts trying to get Ramanujan to Cambridge, but then he hits this huge cultural and religious barrier.
Right. Initially, Ramanujan refused to go.
Why?
He cited his Orthodox Brahmin upbringing. There was intense parental and societal opposition to him traveling overseas to a foreign land. It was a massive, religiously fraught decision. You could lose caste, you'd be forced to break strict dietary laws.
So what was the turning point?
The turning point is one of the most remarkable anecdotes in the whole history of science. It took E.H. Neville, a colleague of Hardy's who was lecturing in Madras, to help convince him. But the final decision came from his family.
The dream.
The dream. The sources say Ramanujan's mother had this vivid, decisive dream where the family goddess, Namagiri Thayer, commanded her to let her son go to England to fulfill his life's purpose.
I love that. A divine mandate that just overrides these deeply ingrained social rules. So this wasn't just a decision, it was a spiritual turning point for the whole family.
It was. So in March 1914, Ramanujan boards the SS Navasa, leaving his wife behind in India. And he set sail for a life he couldn't possibly have imagined. A life that would define his genius, but also tragically break his body.
So Ramanujan arrives in Cambridge, and this incredible collaboration begins. And this is where the tension, but also the real genius, really comes to the fore.
It's a study in contrasts.
You have G.H. Hardy, who is the personification of the Western academic establishment. He's an atheist, an apostle of mathematical rigor, classically educated. For him, it was all about proof, proof, and more proof.
And then you have Ramanujan, Deeply religious, relying almost entirely on intuition and completely lacking any formal grounding in the systematic methods of the day.
Hardy himself was just astonished to find out that Ramanujan had what, the vaguest idea of what a function of a complex variable was.
And that he'd never even heard of fundamental cornerstones of modern analysis, like Cauchy's theorem.
Okay, but how is that even possible? How can a mathematician be world-class in number theory, a field that leans so heavily on complex analysis, but have never heard of one of its most basic theorems?
It just tells you that his mind worked in a fundamentally different way. He was discovering these complex analytical results through a process that Hardy described as a mingled argument, intuition, and induction. A process that, frankly, Ramanujan himself couldn't really explain coherently.
So Hardy is faced with this unbelievable intellectual challenge. He has to mentor this guy, teach him the systematic rules of formal proof, fill these enormous gaps in his education.
But he has to do it without crushing the very source of that extraordinary intuition. It's an incredibly delicate balancing act.
He had to treat him less like a student who needed to be fixed and more like an oracle who sometimes needed translation.
Exactly. It required tremendous patience and respect from Hardy. He was trying to bring Ramanujan up to speed on like 150 years of European mathematics, while Ramanujan was simultaneously leaping 50 years into the future with entirely new theorems.
And the key struggle was just translating that instantaneous, intuitive mathematical truth into the language of rigorous, verifiable proof that the academic world demanded.
And all this is happening during the worst possible time.
World War I, from 1914 to 1918, which just compounded his physical struggle, the silent tragedy of his time in England.
Ramanujan was a strict Brahmin vegetarian. And this is a point that often gets overlooked, but it's absolutely critical.
Maintaining that diet, it wasn't just about not eating meat.
No, it was about abstaining from eggs, fish, often certain root vegetables, and sometimes even requiring self-preparation to ensure ritual purity. This was nearly impossible in Edwardian and especially wartime England.
And wartime rationing made it exponentially harder.
Access to specialized Indian ingredients was non-existent. He was forced to cook all his own food, which took up hours of his time. He became deeply isolated, and that was compounded by the cold, the climate, the relentless intellectual pressure.
His health just deteriorates. He's eventually diagnosed with tuberculosis, coupled with severe vitamin deficiency, which was a direct result of his diet and his isolation.
And yet, despite this overwhelming physical and mental distress, the academic establishment was finally forced to acknowledge his genius.
We see that through this rapid succession of honors. In March 1916, he gets a Bachelor of Arts by Research degree for his massive paper on highly composite numbers.
A paper Hardy later said displayed Ramanujan's extraordinary mastery over the algebra of inequalities.
And then come the historic elections in 1918. In May, he's elected a Fellow of the Royal Society, the FRS, a monumental achievement. He was only the second Indian ever admitted.
And then in October of that same year, he becomes the first Indian to be elected a Fellow of Trinity College, Cambridge.
That swift series of high honors, all within about 7 months, was absolutely crucial. It cemented his legacy. And maybe more importantly, it completely validated Hardy's initial, highly controversial belief in this isolated clerk from Madras.
It proved that even if his methods were unconventional, the depth of his work was simply undeniable.
So let's turn to the mathematics itself, the architecture of his genius. And that distinction between his insight and the formal proof, that remains the core theme.
He was just generating this abundance of formulae that were completely novel. I mean, he was opening up entire new fields of research before anyone else even realized those fields existed.
Let's go back to some of those specific examples to really understand the depth here. We talked about his famous infinite series for Tychus,
which is a highly technical formula based on something called the negative fundamental discriminant $$ equals known as 232.2. It's a complex concept from number theory.
And we noted its speed, its convergence. But let's just pause on what that means for us today for modern computation.
Because that series is so efficient, it's basically the ancestor of algorithms that are being used right now by researchers and engineers who need extremely precise values for pi. His intuitive algebraic structure provided the most practical path forward, even a century later.
Okay, now let's switch gears completely. Let's go from that cold computational rigor to pure instantaneous insight. Which brings us to the famous taxicab number anecdote.
1729.
1729. This story, it takes place when Hardy is visiting Ramanujan in the hospital at Putney, and it just perfectly captures his unique relationship with numbers.
It does. Hardy, trying to make small talk, mentions he arrived in a cab with the number 1729, and he remarks that it seemed rather a dull one.
It's such a beautifully reserved British understatement.
But Ramanujan, despite being severely ill, he instantly corrects him. He says, no, it is a very interesting number. It is the smallest number expressible as the sum of two cubes in two different ways.
That's just that immediate recall and computation. The ability to see the deep properties of a four-digit number instantly is astounding.
And the solution is $1,729 equals 13, plus $129 equals 93, plus 133.
It shows that numbers weren't just abstract concepts to him, they were personal.
As Hardy later recalled his collaborator Littlewood saying, every positive integer was one of Ramanujan's personal friends. He wasn't calculating. He was just recognizing a friend's hidden talent.
And this instantaneous insight wasn't limited to small numbers. It extended to solving entire classes of difficult problems, like the one posed by his Indian colleague, P.C. Mahalanobis, the houses problem.
Right. The problem is a clever one. You imagine a street with houses numbered 1, 2, 3, up to some number nuller.
And there's a specific house, let's call it $6, where the sum of the house numbers to the left of it equals the sum of the house numbers to the right of it.
Mahalanobis had worked out a specific case and asked Ramanujan for the solution. Most mathematicians would spend hours setting up the equations.
But Ramanujan's response was just astounding. He didn't just give the specific solution, he immediately gave the answer as a continued fraction, which solved the entire class of problems, the infinite set of possibilities.
Mahalanobis asked him how he did it, and Ramanujan just said, it is simple. The minute I heard the problem, I knew that the answer was a continued fraction. Which continued fraction, I asked myself. Then the answer came to my mind.
He saw the structure, not the calculation. That's the essence of his genius. And this focus on integers led to what is probably his greatest collaboration with Hardy in 1918, the study of the partition function, PSA9.
Okay, so the partition function, PSA9, it asks a simple question. In how many different ways can you break up an integer nuller into a sum of positive integers?
So for the number 4, for example.
The number 4 can be partitioned in 5 ways. You can have 4, 3 plus 1, 2 plus 2 plus 1 plus 1, or 1 plus 1 plus 1 plus 1.
It seems simple, but as the number gets bigger,
the numbers just explode. The number of partitions for 200 is a number that has 14 digits. It's computationally impossible to list them all.
So how did they solve it?
Their work together yielded a non-convergent asymptotic series, which is a highly complex formula that lets you calculate exactly. And crucially, this collaboration pioneered what became known as the powerful circle method.
Okay, so what is the circle method in simple terms? It sounds very abstract.
It is abstract, but we can make it accessible. Think of a complex number not as a point on a line, but as a point on a two-dimensional plane.
Right.
The circle method is a technique that uses complex integration, basically calculating an area, but on this complex plane, by integrating over a circle. By carefully dividing that circle into what they called major and minor arcs, they could isolate the contribution of specific mathematical properties. It was a revolutionary way of thinking about how to count extremely difficult things.
Using advanced geometry to solve what seems like a simple accounting problem.
Exactly. And even in the last year of his life, when he was frail and suffering, he made one final, crucial discovery that remained a mystery for decades. Mach theta functions.
Yes, this is maybe the ultimate example of his insights being ahead of their time.
He generated these functions, and they were related to modular forms, these mathematical structures with incredible symmetry, but they didn't quite fit the definitions of the time. For years, mathematicians didn't know what to do with them. They were like puzzle pieces from a future game.
So what's their significance today? Where did they fit in?
Well, it wasn't until modern mathematics caught up that we fully understood them. They are now known as the holomorphic parts of harmonic weak mass forms.
Which means?
It means they are specific parts of a much larger, highly symmetric structure that wasn't even fully defined until the 21st century. It just proves that even on his deathbed, Ramanujan was generating insights that were literally 70 or 80 years ahead of the field's ability to classify or even understand them.
When we talk about Ramanujan's immense output, those almost 3,900 results, we have to go back to the physical record of his work, the famous notebooks. And they were filled almost entirely with final results. Virtually no derivations or proofs recorded anywhere.
And this is a huge point of fascination for mathematicians. This lack of proof led to the early and incorrect assumption that he just received the results through divine insight and couldn't actually prove them.
But that's not the case.
No. Brucey Burnt, the mathematician who has spent decades meticulously studying these notebooks, he asserts that Ramanujan most certainly was able to prove the vast majority of his results.
So why the radical omission? Why only record the destination and not the route?
Well, the practical reasons are really compelling, and they speak volumes about his impoverished circumstances. First, paper was extremely expensive in India at the time.
He couldn't afford to waste it.
He couldn't afford it.
Yeah.
So he adopted a common practice for math students in the Madras presidency. He worked out the full proofs and all the complex algebra on a reusable slate.
Which you can just wipe clean for the next problem.
Right. So imagine the physical labor involved. He's not just working out 3,900 results. He's calculating, writing, erasing, and refining these monumental theorems on a slate, and then committing only the final distilled identity to the expensive paper notebook.
That contrast between the physical struggle for resources and the intellectual sophistication is just, it's staggering.
And second, the format was also heavily influenced by Carr's Synopsis, the book that started it all for him, which just stated results without proofs.
Yeah.
He was likely using the notebooks as a personal inventory, needing only the final equations as reference points.
And speaking of records, we have to mention the rediscovery in 1976 of a fourth notebook.
A lost note.
87 unorganized pages containing discoveries from his very last year of life. And its discovery caused a firestorm of excitement among mathematicians. It's fueled decades of work that's still going on today.
It just emphasizes that his output was so vast, so rich, that even the unorganized, messy notes he wrote in the final months of his life contained foundational new mathematics.
And now we have to address the spiritual dimension, because he himself linked it inextricably to his work. Ramanujan was a rigorously orthodox Hindu.
And he credited his mathematical acumen directly to his family goddess, Namagiri Thayar.
For him, mathematics wasn't just abstract logic. It was a way of accessing profound, eternal truths. He often said he looked to the goddess for inspiration.
He even described this vivid dream, similar to the one that convinced his mother to let him travel. He saw a red screen formed by flowing blood, and on this screen, a hand began to write complex elliptic integrals that just stuck instantly in his mind.
And as soon as he woke up, he wrote them down.
It all leads to one of his most powerful and famous quotes. An equation for me has no meaning unless it expresses a thought of God.
And while Hardy, the staunch atheist, really struggled to reconcile this mystical view with academic rigor, there's no question that for Ramanujan, the deep truths of mathematics and divine insight were one and the same. It gave him this unwavering confidence in his results.
It gives you a balanced understanding of his work. His intuition wasn't just a psychological phenomenon. For him, it was a deeply personal spiritual connection that allowed him to bypass the standard process and arrive directly at these fundamental realities.
But despite this staggering flow of insights he was providing right up to the end, his failing health really dictated his final days. The sources note this immense strain of his life in England, which led to a devastating physical and mental collapse.
Including a suicide attempt in late 1917 or early 1918. He tried to jump onto the tracks of a London underground station.
An attempt that Hardy intervened to prevent, which led to his release from arrest.
His illness, combined with the dietary strain and the miserable climate, it all compelled him to return to India in 1919. He was severely weakened, but even back home, he kept working.
He died the following year, April 26, 1920, at the tragic age of 32.
And it's just heart-wrenching to read that even in severe pain in his final days, his wife recounts that he continued doing his mathematics, filling sheet after sheet with numbers.
And what makes his early death even more tragic is the modern analysis of his medical condition. A 1994 review of his medical records suggested his illness was actually more consistent with hepatic amoebiasis,
Which is a serious complication from untreated dysentery, something that was rampant in Madras at the time, not the tuberculosis he was originally diagnosed with.
And if we connect that to the bigger picture, the tragedy just deepens because amoebiasis was treatable.
It was a treatable and often curable disease, especially by the time he left England. If he had received an accurate diagnosis and the right medical care, it is highly probable he would have lived.
The fact that a treatable illness, compounded by the strain of living abroad in wartime, might have been the cause. It's arguably the single greatest tragedy in modern mathematical history.
It is. Yet his work transcended his short life. It laid the groundwork for the next century of math. A major focus of that posthumous work is the Ramanujan conjecture.
This focuses on the size of something called the tau function, which comes from his work on modular forms.
And the Ramanujan conjecture became absolutely central to 20th century mathematics. It was finally proven in 1973 as a consequence of Pierre Delign's proof of the Weil conjectures.
And that work earned Deligne the Fields Medal, the highest honor in math, in 1978.
But the connection goes even deeper. This entire theoretical framework, which sprang directly from Ramanujan's insight, was later essential to the work needed to prove Fermat's last theorem.
Maybe the most famous and difficult problem in mathematical history.
So think about that intellectual flow. A conjecture made by a self-taught clerk, based on intuition in the early 1900s, provided the structural blueprint needed almost a century later to solve a problem that had stumped mathematicians since the 17th century.
That's a legacy that defines the entire field.
And this overwhelming contribution led directly to Hardy's ultimate, iconic assessment of him. Hardy famously devised this scale of pure mathematical talent from 0 to 100.
He rated himself at a modest 25, his great collaborator Littlewood at 30, and David Hilbert, one of the foundational titans of 20th century math, at 80.
And Ramanujan, Hardy gave him a score of 100.
A perfect score, placing him above his own greatest contemporaries. You have to pause and reflect on the sheer magnitude of that, placing a self-taught figure above a giant like Hilbert. It speaks volumes about the raw, explosive power of his genius.
But Hardy's eulogy, which was published in 1940, it was ultimately balanced. He noted both the staggering depth and the glaring limitations imposed by his lack of formal education.
He said Ramanujan's insight was quite amazing and altogether beyond anything I've met with in any European mathematician. He called him the greatest formalist of his time, meaning the best at manipulating complex expressions.
But he also noted that his lack of knowledge was as startling as its profundity. For instance, Ramanujan had to rediscover many known results because he just hadn't read the modern texts. His achievements were greatest in algebra, specifically hypergeometric series and continued fractions.
But despite those limitations, Hardy's final words on his collaborator were so prophetic. He believed that what Ramanujan had accomplished was wonderful enough. When the researches which his work has suggested have been completed, it will probably seem a good deal more wonderful than it does today.
And that prediction has absolutely proven true.
Today, Ramanujan's influence extends far beyond academic papers. He's rightly recognized as a global cultural icon. India celebrates his birthday, December 22nd, as National Mathematics Day.
And the institutional honors are plentiful. There's the Sastra Ramanujan Prize, which gives $10,000 annually to mathematicians under 32, working in areas he influenced. There's even the Ramanujan IT City, a huge special economic zone in Chennai.
Cementing his image as a national figure of intellectual prowess and innovation, and his life story is it's tailor-made for film.
Oh, absolutely. The 2015 film The Man Who Knew Infinity brought his struggles and his partnership with Hardy to a massive international audience.
And even in broader pop culture, his name has become shorthand for intuitive, effortless genius. He was famously mentioned in the 1997 film Good Will Hunting,
where Professor Lambeau compares the main character's raw mathematical brilliance to Ramanujan's.
And he inspired the character Amita Ramanujan in the TV series Numbers, who was also steeped in number theory.
So what does this all mean for us, for the learner trying to grasp the magnitude of his life? If there's one summary takeaway from this deep dive, for me, is that Ramanujan proved that mathematical rigor, while absolutely essential for validation, can sometimes follow intuition and inspiration.
It's a powerful reminder that pure talent can emerge, unstructured and profound, from the most isolated circumstances.
Indeed. And the study of his work continues to yield surprises even now. Bruce Berndt noted that nearly all of the thousands of conjectures he made have been proven correct, often leading to brand new insights.
Which brings us to a final provocative thought, building on the profound depth of his unfinished legacy.
Even the casual passing comments in his notebooks, where he'd remark about certain formulas having simple properties or similar outputs to others, have turned out to be profound and subtle number theory results that remained completely unsuspected until almost a century after his death.
So you have to ask,
what other profound mathematical secrets, entire new fields of inquiry, might still be hidden within those unexamined notes, just waiting for us to catch up to the mind of a genius who lived a century too soon? The exploration is far, far from over.
Thank you for joining us for this deep dive into the extraordinary life and shocking mathematical legacy of Srinivasa Ramanujan.